Now, one thing you might not know is that the positions the planets in the solar system are in today haven't always been that way. So the place that a planet formed isn't necessarily the place it's ended up, just due to the complicated interactions of gravity between all the planets, comets, asteroids, and bits of rubble left in the solar system. And it turns out that it's my favourite planet, Saturn, that made the difference between Earth ending up in the nice Goldilocks zone around the sun, where it's, not too hot and not too cold for life to start, where we are now, or being flung out into the icy cold depths of interstellar space. So to understand why this is, and to understand this, whatever it is, 389th reason why Saturn is my favourite planet in the solar system, we have to understand how the solar system formed. And you might be wondering, well, how in the universe did we even figure that out? And it came from sort of a combination of a couple of different things. The first is just observing the solar system, like noticing where we find certain types of objects, like asteroids, and where we find certain types of planets in the solar system too. The second is from looking at other star systems in the Milky Way. So that's looking at other planets orbiting around other stars in our galaxy. And the third is by running computer simulations, so simulations of all of these interactions due to gravity of lots of planets forming around a star. So when we observe newly formed stars in the Milky Way, we see them shrouded in sort of lots of dust and gas. And usually that starts out life as sort of a sphere around the star, but the star, when it starts to form, is spinning. And so just like when you take a ball of pizza dough and you throw it up above your head and set it spinning and it flattens out into a flat disk, the same thing happens around a star, and all that material condenses into a flat disk. And that's why the solar system, all the planets, are in sort of that same plane, because they formed from this disk. And they formed from the debris that can be anywhere from sort of like nanometer-sized chunks to sort of centimeter-sized chunks that get attracted to each other by gravity, and over time very slowly clump together to give you what we call a planetesimal, which is usually sort of like kilometer-sized chunks of rock, kind of like, asteroids and comets and stuff that we see in the solar system. From these planetesimals in computer simulations, we see a runaway build-up under gravity into fully formed planets. Now, close into the star, there's just less material there, right? Because there's just less volume of space for you actually to put that material in. So the planets that form close into stars tend to be a lot smaller, just because there is less material there for them to form out of. They also, though, tend to be formed of heavier elements and metals like carbon and iron, for example, because those elements have sunk towards the center of the system under gravity. Further out, though, there's a lot more material, so planets can grow a lot bigger. And we find that when they start to hit about 10 times the mass of the Earth, they become heavy enough to start actually attracting the hydrogen and helium gas that's still available in this sort of like disk of rubble around the star, the gas that really didn't go into forming the star. They start to attract that. And that gas, if it's cold enough, can condense onto the planet, i.e. it can form this like atmosphere, usually very, very thick atmospheres of this gas, to give us things like the gas giants of Jupiter, Saturn, Uranus, and Neptune. And so that really nicely explains sort of what we see in the solar system, right? Where we have the smaller rocky planets of Mercury, Venus, Earth, and Mars close into the sun. And then we have the much, much bigger gas giants of Jupiter, Saturn, Uranus, and Neptune much further out. So that was sort of the agreed upon scientific explanation for how the solar system had formed for many, many years. But it wasn't really until we started observing other planets around other stars in our galaxy that we realized that that story just didn't add up anymore. And it was because of these very strange planets that we were observing that we realized this. So anything from rogue planets, planets that aren't orbiting a star at all, they're just sort of freely floating through interstellar space, or to planets that don't all orbit in the same plane in one system. You might have one planet that's orbiting the pole of the star and the other planet that's orbiting sort of around the equator, and it's just this big chaotic mess. Or you've got planets that are on huge oval-shaped orbits that take millennia to orbit their star. There's these huge elongated things, kind of like what we see the orbits of comets in our own solar system. But the biggest challenge to this idea was hot Jupiters. So the majority of planets that we detect around other stars are hot Jupiters, i.e. they are Jupiter-sized or bigger, but they orbit so close to their star. They're sometimes even sort of within the distance that Mercury is to the sun around their star. That doesn't make sense under the sort of the idea of how we think the solar system formed, because it's far too hot there for the gas to condense onto the planets and make those huge big gas atmospheres like what we see with sort of the gas giants out in our solar system. But also there's just not enough material around the star to make a planet that big very close in. And so the idea that's been proposed to explain these hot Jupiters and lots of other things that we see in star systems that we observe, that was sort of proposed in 2005 and has slowly become accepted sort of theory by the sort of science community of researchers who work on this, is the idea of planetary migration. The idea that where a planet forms is not necessarily where a planet ends up. So it's very likely that these hot Jupiters actually did form quite far out from their star, but then have migrated inwards to be very close to them. I guess the remaining question, though, is why has that happened? Well, one idea is that as these star systems form and you start building up these planetesimals of sort of kilometer-sized chunks of rock and material, star systems look a bit more like the asteroid belt in the solar system rather than sort of having these very sort of like separated out planets. And if you have a system that looks like that, then there's going to be a lot more interactions between two objects as they either collide, which we think is how they build up their mass, or maybe even just fly by each other. Now, in those kind of flybys, the two objects actually exchange energy. And how much energy, is exchanged from one to the other really depends on how big the objects are. So the smaller objects in that sort of flyby and exchange usually gain energy. We usually often use this as sort of what we call a gravitational slingshot if we're trying to send a probe out to the far reach of the solar system. We can sort of slingshot around Mars and it can gain some energy to get it way out to the edges of the solar system. The same thing can happen if sort of two lumps of rock meet each other as well, right? So the smaller object gains energy, and that means it can actually be slingshotted out of the system entirely, perhaps causing these rogue planets, or perhaps putting the object on these really, really long, elongated, oval-shaped orbits around the sun, the same sort of kind of orbits that comets have, that take, millennia to go around. But what also happens in those interactions is that the larger object loses energy. And so if the larger object loses energy, what then happens is that it starts to sort of sink towards the center because of gravity. You've got the much larger star then pulling on it more as it loses energy. Now, when this model of planetary migration was first proposed back in 2005, its main idea was to explain the hot Jupiters that we were seeing, but people quickly realized that if this had happened so often in other star systems in our galaxy, then surely it must also have happened in our own solar system as well. And so this is where sort of the computer simulations come into it. And so if we try and match what we see today with lots of different initial conditions and what could have happened in the solar system, we build up this picture of what is the most likely thing that has happened according to sort of our simulations that take all the laws of physics. And what we find is that, first of all the gas giants probably formed first, before sort of the terrestrial planets of Mercury, Venus, Earth and Mars. And yes, they did indeed migrate inwards. And that migration inwards saw them encountering so many sort of random bits of rock and rubble on their way in. And this is probably what's caused, the comets to be on such elongated orbits around the sun. But also those interactions probably ejected a load of those objects from the solar system as well. A huge number of them. Who knows how many of them, since that happened maybe 4 billion years ago, have actually encountered another star in their lifetimes now, in the same way that we had the interstellar visitor Oumuamua back in 2017 that we think was one of these sort of ejected objects from a newly formed star system at some point. But the simulations also show that Jupiter probably migrated in to about the distance that Mars is from the Sun today. And if it did that, it will have cleared out a lot of those planetesimals from that area. So that probably explains why Mars is so small for its position in the solar system. So Venus and Earth are roughly about the same size and mass, but Mars is probably about half the size and only 15% of the mass of Venus and Earth, probably because all those planetesimals that it could have used to grow much bigger were thrown out onto much more elongated orbits or even out of the solar system entirely by Jupiter. It also explains why the asteroid belt is where it is between Mars and Jupiter, because if Jupiter crossed this region, it has such a strong influence on the gravity of that region that it will probably have stopped all of those planetesimals, what we call asteroids today, from clumping together to form a new planet. But obviously the big question is still, why didn't Jupiter go any further? And why now has it been pulled back to the position that it's in today? And you might be wondering, well, why do we care? And the reason that we care is because if it had gone any further, it would have definitely disrupted Earth's development into a planet and maybe even thrown out all of the proto-Earth material into interstellar space, just killing all chances that life would develop on it. Now, as you've probably guessed, the reason for this and the reason that we are all here today, me making this video, you watching this video, is because of Saturn. Let's look at it again. Oh, it just never gets old. It's just so gorgeous. So as Jupiter and Saturn both migrated inwards at the same time in towards the Sun, they ended up in what's called a resonance about when Jupiter hit that orbit of Mars. It was a 2-to-1 resonance to be precise. And what that means is that for every 2 orbits around the Sun that Jupiter makes, Saturn makes 1 orbit. And it's a very stable sort of position for those planets to be in. The gravitational forces are really nicely balanced. So it's very difficult to break that resonance once they're in it. We see this actually when we look at a lot of other star systems of planets as well. We see them in resonances, and it's quite cool actually, because if you get a system where all the planets are in resonance, like a 2-to-1, a 3-to-1, 5 and a 7-to-1 sort of resonance all on a chain on the way out, you can sort of make each planet sort of play like a note every time it goes around once around the star. And then sort of again, when they sort of all line up and resonate together, they play the notes together. And it makes this really interesting music that's sort of made out of nature, which I absolutely love. Like, listen to this system. So Saturn essentially sort of held on to the reins of Jupiter and stopped it going beyond the orbit of Mars because of this resonance. But as I said, these resonances are very hard to break, and yet we know that Jupiter is no longer sort of at the orbit of Mars, it's much further out, and Jupiter and Saturn are no longer in a resonance. So what we think eventually broke that resonance was then the interaction with Uranus and Neptune also migrating inwards as well. This sort of added interaction due to gravity combined with sort of breaking that resonance forced Jupiter and Saturn's orbits to become much more oval shaped and circular. It pushed all of the planets back out again, far away from the Sun, where they also interacted with all the sort of icy bits of rock and planetesimals left at the outside of the solar system, pushed them way out into what we call the Kuiper belt today, way past Neptune, and eventually the gas giants sort of settled back down into those roughly circular orbits that we see them in today. Now, although this model reveals a lot about our own solar system and explains a lot of the things that we've seen in other planetary systems in our Milky Way galaxy, there's still a couple of things it's not quite been able to explain yet. And one of those is, why more star systems aren't in resonance with each other if these resonances are so stable. When planets reach them, it's very difficult to break if they've been migrating all over the place. And so is it just that there are other planets in these systems, maybe that we haven't spotted yet with our methods of detecting planets, that will have interacted with them to break these degeneracies, or is it something else entirely? The big question for me is why these hot Jupiters stopped migrating inwards where they stopped, right? In sort of that Mercury sort of distance-ish from the sun. Like, what stopped them from just spiraling in and being completely destroyed by their star, right? Maybe it's just that we're actually seeing a snapshot of this sort of migration inwards, right? And we're seeing it at a specific point. And if we watched for long enough, for centuries or millennia or whatever it would be, we would eventually see these planets sort of get consumed by their star. Or maybe there's some reason that they did get halted there. Maybe, again, it's something to do with sort of these complex interactions due to gravity between all of the objects in these systems that somehow halted them right in close to their star. I mean, like most things in astronomy and astrophysics, it's, more data is needed, more time is needed to observe them, as always. And that will come with, we've got the launch of the TESS telescope that's gone up in the past year or so. That's like the follow-up of the Kepler Space Telescope. Literally about 4,000 planets plus were detected with Kepler. It's one of the most successful missions ever. Then you've also got the launch of the James Webb Space Telescope in 2021 next year, fingers crossed. And the exoplanet community are very excited for that, because that's going to help them characterize the atmospheres of these planets that they're looking at, and perhaps sort of probe, what's in these big hot Jupiter atmospheres. Is it similar to the solar system or not? I'm very excited to see what will come out of all of these sort of observations and missions that are planned for the future, and what we will be able to learn maybe about the origins of our own solar system and origins of our own planet here on Earth too. And perhaps maybe, just maybe, we'll learn one more reason that I can add to my ever-growing list of why Saturn is my favourite planet. Before we get to everybody's favourite part, the bloopers, I just want to say a big thank you to this week's video sponsor, which is Brilliant. Brilliant is a website with courses on all areas of science and maths. And the courses are fun, they're interactive, and most importantly, they get you to learn by doing. So they break down a very complex topic into chunks that are easy to understand and easy to remember. Now, Brilliant have a big astronomy course collection too, including courses on star formation from, these gas and dust disks that we spoke about in this video, to the different methods that we use to find exoplanets, planets not around our sun, but around other stars in our galaxy, the Milky Way. These courses are so great because they don't just teach you about planets, but also about how telescopes work, going through their limitations so you can work out what is the smallest thing that these telescopes can see, and therefore what exoplanets can we spot. If you like the sound of that and you want to support me and my channel, then head over to brilliant.org/Dr Becky. That's DRBECKY, and sign up for free. Plus, the first 200 people that go to that link will also get 20% off their annual premium subscription. So go forth and learn something with Brilliant. Thank you very much, Brilliant, for sponsoring this video. And now, those bloopers. Oh, it's that time again though, isn't it? Like, just place your bets now, people, on how many comments there's going to be on how I pronounce Saturn. Like, yes, grammar police, I know there's a T in the middle of it, but it's my accent. But it wasn't until we started observing other stars in our... But the models also show. Whoa, I'm an alien. I'm a legal alien, I'm a Jupiter in real clothes. Whoa.